Welcome to the third video on combined stress. In this one, we finish setting up our equations for the normal stress, and we set up the equations for the shear stress. These equations are not set up as to be specific to either point A or B, though I suppose you could do that. Have fun! Now that we've determined these equations for the normal stress of our cross-section, we need to consider the shear stress of the cross-section. So we're going to have those also be, some of them, functions of our distance from the neutral axis and from various places. So let's start with torsion. Right, so the torsion equation is that the shear stress is equal to the torque times the radius divided by the polar moment. In this case, we will have 2,500 pound-inches divided by half of pi, 1.57 inches to the fourth, times whatever your radius is at that point. That's going to be 1591.5 pounds per cubic inch times rho. Now in both cases, we're going to have 1 b rho, but it will cause different directions. This has sort of an asterisk next to it because you do have to be careful with shear due to torsion, looking at which way it's going, right? Because on the right it might be going up, but on the left it's going to be going down. So this is from the torsion. But we also are going to have shear due to transverse shears in both the y and z direction. So from the shear in the y direction, we're going to have this equation. It's the equation that shear is equal to Q times the shear divided by your second moment times your thickness. Now, Q is obviously a function of where you are, so we can't really do that. We can get rid of shear and the second moment of inertia, though, because this is going to end up being 600 pounds for shear in the y direction, and divide that by 0.785 inches to the fourth for that, times Q over T. That gives us 764 pounds per quadric inch times Q over T. So we can just plug in whatever values we want for Q and T and solve. Similarly, for the shear in the z direction, we have exactly the same thing, right? It's going to be Q times T, except for now, this time, instead of progressing from top towards this neutral axis right here and then going to 0, we're going to progress from maybe this point towards this axis and then back to 0. And that's so that's going to be 400 pounds divided by second moment of inertia, which is 0.785 quadric inches times Q over T. And that will give us a value of 509.6 pounds per inch to the fourth, and that's times Q over T. So now we have now we've got all of our 6 equations into a very readable, sort of legible form. Let's consider first point A and then point B. Point A is, as we observed, at the top, and point B is on the side. But we've got many distributions of stress, 6 distributions of stress to consider. We can use superposition to find what the stress is. At any given point, we've picked A and B.